understanding of basic AI stuff is now part of the expected tool bag of any computer professional. So, if you're going to be a computer professional, you got to know something about artificial intelligence. And there's another reason too, and that is it'll make you smarter. And smarter in interesting and fundamental ways. Won't add brain cells, but it'll equip you with ways of thinking about thinking that will make you smarter. So that's a second reason then why it's a good thing to look at this stuff from artificial intelligence. So having said that, I want to show my hand right away and tell you what I'm going to tell you. I'll tell you what my goals are. And my goals are to equip you with all of this kind of stuff. Certain skills, ability to build certain kinds of systems, and understanding of certain concepts that lie underneath those systems. So you'll learn how to build rule-based expert systems today. In order to do that, you have to have a concept of problem reduction. Tomorrow we're going to talk about building resource allocation systems, which will require an understanding of search and constraint. After that, we're going to spend a couple of days on learning systems, which will in turn require their own kinds of conceptual understanding. And then as a veneer across all that stuff, I want to equip you with an idea of what this is all about anyway, and why it's valuable. So that's our purpose, and that's what we're going to do today and the next 3 days. So if it's valuable because it's an expected part of any computer scientist toolkit, and if it's going to make you smarter, then we better know right away what kind of definition we're going to use for it. There's probably a definition for every practitioner, so we could spend 4 days talking about definitions. But I don't need to do that because I can talk instead in terms of my definition and wrong, and the rest of the wrong definitions. It'll be my definition because I get to talk. So here's the definition. Artificial intelligence is about computations that connect perception to action. That may strike you as a little odd because it could be, you might think, well, that's the definition of robotics. We're not going to talk about robotics. Ultimately, if you think about the science side of AI and what thinking is all about, I believe it grounds out in computations that connect perception to action. But that's a kind of philosophical point. So for people interested in stuff that can be used, I have to modify a definition a little bit and maybe include reason and maybe learn and connect perception to action. So that's what it's going to be from our perspective. Computations that reason, learn, and connect perception to action. So in some sense, it's about human intelligence too, but doesn't have to be. But when human intelligence informs us in our enterprise of understanding connections that connect perception to action and learn and reason, then we can think of much of AI as a kind of crystallized human intelligence. Stuff we do every day, given a name. And it's not just that giving it a name glorifies or anything, but giving a name makes it possible to talk about it. So some of the stuff that you do every day can be given a name, which enables you to talk about it. So in spite of the fact that it's sort of obvious, it's still valuable to crystallize it and give it a name. So I'd like to give you an example of such a computation that's been given a name in AI that enables you to recognize stuff. It's the idea. God, the center of gravity is pretty much over there. It ought to be over here. Well, we'll put $5 bills on these chairs tomorrow. It's the idea of generate and test. And the problem is you want to recognize something. Maybe you want to recognize a tree. And you got a leaf. You know how to do it, right? You go to the store, you take your leaf and your copy of the Guide to American Trees, generously published by the Audubon Society, and you start thumbing through it page at a time until you find a match between the leaf and a page in a book. That's what you do, right? This leaf happened to come from that plant over there. I hope it's not the last species. But normally that works just fine. So it's not just something obvious to do, but we give it a name, and we'll call it generate and test. So a sort of logo for this is that there's a generator and a tester. And out of the generator come possibilities into the tester, and most of them go into the garbage can because they don't match. And eventually one pops up, and that's our identified plant, tree, whatever it is. So that's the metaphor of generate and test. It's a very simple thing. It takes about 2 minutes to explain it, but now it's now part of your problem-solving apparatus. You can say, well, we're going to solve this problem with generate and test. And now you can talk about the properties of the generator. You can say, for example, you'd like your generator to be complete. So if there's a tree, you'd like it to be in the book. Right? What else what other desirable properties are there of the generator?
Non-redundant.
Non-redundant. You don't want it to be you don't want to generate the same solution over and over again. As you could, for instance, if you built a program that just offered up a page from the book at random over and over again. That would be a redundant generator and diminished in its redundancy. And finally, you'd like this generator to be informable. So if you've got a leaf like that, you don't want to look through all the conifers, because you can inform the generator that this thing is a deciduous tree, plant, and therefore it doesn't make any sense to offer up the stuff from conifers. So now you have the first of the entries in your AI toolkit. It's a computational scheme for doing some reasoning. In fact, in particular, that kind of reasoning has to do with recognizing something. In this particular case, when you do this with a book, the generator is the book, and the process of generation is leafing through the book, and the testing is done in your eye. And that's how you do generate and test every time you use a tree book. So it's an example then of this definition. But I'm unhappy with this definition, even though I use it for many years now. So I'm going to give you a slightly different definition for the first time, because I don't think this is quite right. It's not quite right because I don't think it puts the right slant. It doesn't give us a way of thinking about artificial intelligence that ultimately allows us to see a red thread, as the Europeans often say. It doesn't give us a way of seeing some thread that runs through the whole subject. You've seen that before when you talked about programming, right? Scheme. That's the red thread that runs through a scheme course. Abstraction. It's about one thing. It's about abstraction. One of the four powerful ideas that make building big systems possible. This definition doesn't lend itself to that, because if this is all you have, then what you get at the end of 4 days is a feeling you've got a tool bag of very different tools with no common theme that runs through them. So I'm going to expand a little bit on this definition. And I'm going to say artificial intelligence is about representations that enable those computations. And ultimately what you'll see is that there are a small number of representations that are really the underpinning of practical artificial intelligence. What's an example of a representation? Well, when you were a kid, you all solved this problem with the farmer, the fox, the goose, and the grain. They've got to get across the river. The boat will only hold 2. The goose, if left alone with a grain, will eat it. A fox, if left alone with a goose, will eat it. So your problem is to get everybody across the river. So you have to worry about how to represent the problem. When you were a kid, you solved it, but it's sort of by blind operations. I wish I had to solve it right. So when you're a kid again, you'll be able to do this instantly and impress your parents. Well, we could talk about the color of the goose, how white it is, and the speed of the fox and its cunning. But that wouldn't be right? Because that wouldn't help us to get these guys across the river. So we've got to find a representation that exposes the right stuff and sort of suppresses the wrong stuff. So what's the right stuff? Well, let's just write down there's a farmer, there's a fox, there's a goose, and there's some grain. And there's a river in between them and where they want to be. So that's a representation of one possible state in this little system of the farmer, fox, the goose, and the grain. And there's another state that we could represent that looks like this. Here's the river again. Here's the farmer. And here's the goose, the fox, and the grain. That's another state of the system. So now we've got a representation that's pretty good because it's making the right things explicit for us. At some point I'll write all this down because it's understanding the characteristics of a good representation is where much of the problem solving that humans do when they create an intelligent system lies. In fact, let me make the following emphatic claim. Once you've got the representation right, you're almost done. Once you've got the representation right, you're almost done with the problem. And this is the right representation. At least it looks like it might be the right representation for the farmer, the fox, the goose, and the grain, because it's made the right things explicit. But now, what makes it? It's got some stuff that's explicit where everybody is, but it still isn't quite enough because we haven't used the representation to dig out something that's going to be valuable to us in solving the problem. And that's the constraint. We know, according to how we set up the problem, that there's a possible transition between those two states because the farmer can load up the goose and take it across the river. Fox won't eat the grain, and the goose won't. The goose isn't anywhere near the grain. Fox can't eat the. So that's a possible transition. It's something the farmer can do in one step. So maybe we're not quite through with this definition yet. Maybe we need to say it's about the constraints exposed by the representations that enable computations that reason, learn, and connect perception to action. So now we ought to fill out this diagram just to have one complete little solution to a problem based on a good representation in front of us. And I'm just going to draw these other states in miniature so you can see what the whole graph looks like. This is now representation with a representation that exposes the constraints of the problem. That's the full diagram of the farmer, fox, goose, and grain. Every possible state is there in which nobody gets eaten. Let's see, everybody can be on one side of the river or the other. So how many states are there altogether? 2 to the 4th, I guess, right? 2 to the 4th. I guess there are only 10 there. Must be the 6 other states that involve somebody getting eaten. So now we've got an expanded definition of what AI is. But you know what? It's not quite enough because in the end, this is the desired state, by the way. I haven't drawn it all out, but that's the state in which everybody's on the other side of the river. And now how do you get from one end to the other? Well, we're humans. We can use our eye to find a path through this graph. So, boom. We can tell, incidentally, that there are exactly 2 solutions because our eye instantly tells us that there's 2 paths through this graph. So maybe what artificial intelligence is about is algorithms, the constraints exposed by representations that enable the computations that connect, that reason, learn, and connect perception to action. And now we're done. That's what it's about. But fundamentally, what it's about is this item right here. That's what's right in the middle. It's about representations. Everything else is about the constraints that the representations expose and about algorithms that you can use once you've got the constraints. But the thing about algorithms is that, a set of constraints will generally emit all sorts of algorithms. And it doesn't really matter which algorithm you use. What matters is the fact that there's a constraint there just lying in wait, waiting to be exploited. All right? So that's how to think about artificial intelligence. It's about a certain kind of constraint. Algebra is a constraint, right? It shows you how to constrain things. So artificial intelligence is about a set of constraints that make it possible for us to build systems that appear to be intelligent. And that's what, as computer professionals, the enterprise is all about. All right, so that's where are we? It's important. Why? Well, it's important because it's part of the expected toolkit of every computer professional, and it'll make you smarter. And here's our definition. And now we're ready to plunge in. Except I want to take one more kind of detour and give you a little bit of sort of cocktail party discussion of the history of the field, just to show you where it's come from, how long it's been around, and what therefore the context of this discussion is. Now, this is going to drive me nuts. I have to tell you, there's an amazing amount of feedback that occurs between an audience and a speaker. I have 350 students in my class at MIT, and it's very interesting that how the audience can affect the way I talk. And funnily enough, it isn't just the audience as a whole. It's usually just one or two people who are sort of the outliers on the curve. And if they're smiling, like Chris is here, that creates a very positive ambiance. And if they're sort of asleep in the front row or frowning like mad, that has the opposite effect. But this is not a surprise because the psychologists, of course, have done a lot of work on this, and in particular there was a Professor Verplank at Harvard who did a lot of work on non-verbal communication. And one day a graduate student was talking to Verplank and happened to pull on his ear like that, and Verplank suddenly had an inspiration and he nodded. And so nothing happened for the conversation. Then the kid pulled on his ear again. Verplank nodded again. So by the end of this discussion, the kid's ear was bleeding. And Verplank said, "What's the matter with your ear?" He says, "It itches." So Verplank's graduate students got wind of this, and pretty soon all over Harvard Yard, students were wandering around with all sorts of tics and halts as a consequence of this kind of training. But in particular, there was a mathematician who the students decided to hack. This mathematician had a habit, as I do, of walking back and forth in front of the class. So they decided that when the professor walked to the left, they would all smile and nod. And when the professor walked to the right, they would all frown. So you can guess what happened. Pretty soon the professor was lecturing from approximately this position, slightly outside the classroom. But you know what? This is a long story because I like a few of you kind of do a right shift here, because otherwise I'm going to be off out by the Coke machine. So could you just kind of pick up and top 5 of you kind of wander down there? That'd be great. This way Seth won't have to come up with the $5 bills. So when did this field begin anyway? Well, some say it started with Aristotle. But the modern history of artificial intelligence started with Turing in the late 40s when he laid out the Turing test. You may want to do a 90-degree rotate here for a few minutes because I'm going to be working the slide projector for a while. We need to turn off this one. No, the screen light.
Oh, turn off the screen light?
Yeah.
Oh, because yeah. Hold it in for a second. Let's turn that. We need to turn that on.
Yeah, I'll turn that on. I can manage that one. Let's see if we can. I know it is middle of the night for many of you, so try to keep the lights up as much as we can. So that was Turing, who sort of told us how to determine whether we're successful or not, sort of. But the modern history of artificial intelligence really started in 1960, when a blind student, Marvin Minsky, wrote a program that does symbolic integration. His name is Jim Slagle, and he wrote a program that could do integration problems in a manner that was meant to capture the way students do integration problems. And he was successful in building a program that got a unbelievable A on a set of 54 MIT calculus final examination problems. It's a model for us to this day. It was the first expert system. We didn't know it at the time, but it was a rule-based expert system, and set the stage for people speculating about how long it would take for computers to achieve human-level intelligence. We can call this the dawn age of artificial intelligence. In fact, perhaps it would be good to just draw a little timeline on here to keep track of where I am. You can divide the last 50 years up into some decade-long pieces. So Turing came along in about 1950, and we're in about 2000 now. So this was 1960, the dawn age. And it was about that time that another student of Marvin Minsky's wrote a program that solved geometric analogy puzzles, the sort that are often on intelligence tests. A is to B is C is to what? Remember solving all these? Oh, by the way, what's the answer? A is to B is C is to 2? Is that right? 4? Well, the program said, see, I can't actually solve these problems myself, but I can simulate the program. So when I simulate the program, I say, well, let's say it looks like we delete the inside object, which makes it 2. And if 2 weren't there, my theory would be that it deletes the outside object and expands the inside object, so the second best answer is 4. And this, too, is meant to model some kind of human problem solving. But, of course, the most famous program of this dawn age was the ELIZA program that pretended it was a Rogerian psychiatrist. Some say it said more about Rogerian psychiatrists than it said about AI. It's probably the most rewritten program of all time. So that was the dawn age. And that was followed by a dark age. Nothing much happened in the late 60s. Problem was, this stuff was too good. It made everybody think that it would be possible to build a program that was so smart it could make itself smarter and start a kind of AI chain reaction. Too bad for our side, it didn't happen. And we sort of know why, but it didn't happen then. It led a lot of philosophers to speculate, well, it can't happen. So there was a lot of dispute between AI scientists who are trying to be good guys and alert the public to this danger, and the philosophers who were saying, see, we told you so. But in any event, around 1970, there was a sort of renaissance. Spelled approximately right, I hope. And there were several programs that were said to constitute this renaissance. I wrote one of them. It was a program that learned about arches. So you showed it some samples and some near misses, and up it came with a theory of what it means to be an arch. The one that got a bigger splash, though, was a program written by Terry Winograd. Had to have a name last name starting with W in those days. Winograd wrote the Shirley program that carried on a conversation about a simulated blocks world, and was able to disentangle even convoluted sentences like that. Does the shortest thing that tallest pyramids support anything green? You can do that. I guess you can do that too, but you have to put parentheses around it to parse it. And the answer is yes. So the third of the W's, all of us students of Martin Minsky, was Dave Waltz, and he wrote a program that could look at drawings and figure them out. It could tell how many blocks there were, and it could tell which direction the surfaces were pointing. And it had even the following wonderful property. It had the property that if you didn't give it some of the edges, it would start seeing these things the same way we do, as ambiguous. We can see that as either a bunch of saw blades sticking up or as a bunch of staircases leading up, right? So you all see that reversal. So that was the Renaissance. Then, once again, nothing happened. We got stuck again until sort of the middle 70s, right around in here, when the late David Marr introduced a sort of revolution in artificial intelligence, which said, well, those people who are interested in the science side of AI should be interested in ecumenicalism. I won't even try that. He was a mathematician by training, a cognitive scientist by instinct, and he wanted to understand human intelligence. He wasn't interested in applications. He was interested in human intelligence and in explaining computationally phenomena like this. There's some random dots. You see that flow pattern? You can amuse small children with this sort of thing. And then if you go enough, the pattern breaks. He wanted to understand that. And he also introduced a lot of methodology into artificial intelligence that survives to this day, even though its origins are lost in history. But about that time, artificial intelligence had been around for almost 20 years. And back in the beginning, we said, don't bug us for 20 years. We'll find applications then. And so, whoops, 20 years passed. And so people started to say, what happened to those applications? So around the middle of the 1980s, we had the first wave of AI applications, AI biz. And much of that AI biz was enabled by rule-based expert systems technology. The program that started it all was a program written at Stanford for doing medical diagnosis. This program could diagnose infectious disease of the blood better than most doctors. Not as well as a specialist, but better than most doctors. Curiously enough, this program never saw any commercial use, mostly because doctors don't give much of a damn about what's actually wrong with you. They just give you a broad-spectrum antibiotic and get on to the next patient. But this program could tell exactly what's wrong with you on the basis of evidence at hand without waiting 2 weeks for a culture to develop. So this was the Mycin program, launched the first wave of venture capital interest in artificial intelligence, grew the big AI biz, which was a good model for what has subsequently happened to the dot-com biz. But then there's another age that comes along here just before the 1990s, and that was the diaspora. People said, well, we need a new way. We need neural nets, we need genetic algorithms, we need agents or something. And so artificial intelligence split into a whole bunch of fragments in an effort to deliver on the promises of the early days about how artificial intelligence would be useful. And sure enough, it has been. And now we have the AI biz number 2, second artificial intelligence biz, which is less conspicuous but more important. And it's less conspicuous but more important because ultimately, artificial intelligence become part of the fabric of every big system anybody builds. The most famous person in artificial intelligence in 1975 was George Heilmeyer. He was the head of DARPA at the time and a severe critic of artificial intelligence. He thought it would never amount to anything, shut off a lot of funding for it as director of ARPA. I saw George, I think it was 1998, after he'd been head of Belcor and had a very distinguished career doing all sorts of stuff. He's an incredibly smart guy. I have great respect for him. He looked at me and said, "You won." I said, "What do you mean, George?" He said, "You cannot build a big system today that doesn't have elements of artificial intelligence in it." So in that respect, artificial intelligence has become just part of the general fabric of computer science. It's in every system, but it's not so conspicuous. Because you don't build AI systems anymore. You build systems with AI in them. Just like you build systems with relational databases in them, or web access in them. Just something you got to have. And you can still, nevertheless, find those applications, even though they're under the covers, if you look a little bit. So I want to conclude this history with showing you just a few examples of where AI is buried. There's AI in that little paperclip. Now, if you don't like the paperclip, let me tell you that it would be even worse without AI in it. It's based on Bayesian net stuff, generally regarded as a part of artificial intelligence. And it solves all sorts of problems. I found that I've only asked it one question, it nailed it. You guess what the question was? How do I turn you off? But it's an example of something that does a little bit of good for a lot of people. Let me show you something that's symmetrically opposite of that. It's a program that does a lot of good for a few people. It's a program which I characterize as a program that's given X-ray vision to surgeons. Basically what it does is it takes an MRI image and registers it with an ordinary image. So we can take an MRI image of your head one day and put it in registration with your face on another day. So now the surgeon can sort of turn a crank and see what's inside your head. And this is extremely important because as you undergo a brain operation, you're moving around a lot. Not because you're moving, but because the table's moving. It lasts several hours. The surgeon's got to move you up and down just so they don't get too tired. So using this kind of technology, it's easy to quantify the value. It turns out that the surgeons can operate on 30% more patients. That is to say, it's brought patients within the sphere of operability because you know precisely where stuff is and it's not so dangerous to do it. And the other thing is it gets people off the table about 30% faster, which has a profound effect on mortality. And then I suppose there's this one, which has done a lot of good for a lot of people. The great wave of lay people who want to use computers but don't know how. Ask Jeeves enables them to ask questions on their own terms and get answers. And it's reasonable to say that this is enabled as a consequence of stuff that's happened in artificial intelligence. My own company does software for airlines and airports. So if you ever fly through Atlanta, your aircraft will be parked at a gate selected by an AI program. Or if you fly through Oslo or Copenhagen or Kuala Lumpur or points all around the world, many of the resources will be managed by programs written by my company, of which a small fraction of the code is enabled by AI technology. It's like raisins in a loaf of bread, to use a metaphor I originally heard from Esther Dyson, a noted commentator on the world of computer business. I like the metaphor because raisins don't occupy much space in the bread, but you can't have raisin bread without the raisins, and they provide a lot of the nutrition. So it's a good characterization of many programs that have AI in them these days. It doesn't occupy a whole lot of the code, but it makes the program possible. It's like raisins in a loaf of raisin bread. So the AI in the systems of Ascent Technology, my company, are present like raisins in a loaf of bread. Makes a lot of stuff possible. So that's a little bit of history of AI and where it's been and some of the ages that it's gone through. And so you might say, well, what's next? This is a confusion of science-side AI and business-side AI. Starting off with science-side AI, trying to understand the nature of intelligence and human intelligence in particular, and gradually over a period of time reorienting itself mostly in a business direction, trying to build systems that are smarter. So if you ask me what's next, I would say in the business side, more of the same, and on the science side, a revolution. I believe that within the next 10 years we might have the analog and artificial intelligence of the discovery of the structure of DNA in molecular biology. A revolution that could really enable us to understand the nature of our own intelligence in a new way. But this is mostly not about philosophy, it's about really doing stuff. So let us leave the science side aside for the moment and carry on with a discussion of the business side and representations that make all that possible. First thing to talk about in that context is the concept of the rule-based expert system. Myson was a rule-based expert system. The program that did integration was a rule-based expert system. But the program that started that first wave of AI biz activity was the XCON system, now disappeared into history. But shortly before you were born, the XCON system was conceived. This is one of the days when computers occupied several refrigerator-sized cases, right? So if you ordered the equivalent of a weak PC, it would come in 3 or 4 of these cases, and you need a whole bunch of power supplies and cables and stuff, and you ordered the memory separately, and there were these guys who specialized in figuring out what you needed, and then there were other guys at Digital Equipment Corporation who figured out how to package it, how big a power supply you needed for all that stuff, how long the cables should be, where they should put the stuff in the boxes. That was all figured out by humans, and they'd screw it up every time. So here you are, you're in Sydney. You ordered this computer from Digital Equipment Corporation. All these big, wonderful boxes come, and you're missing a cable. It drives you crazy. So about this time, the Myson system had been written, and some smart guy said, well, maybe we can build a rule-based expert system that will configure computers. We'll save money because we won't have to employ the people who do it, and we'll have less customer irritation because we'll get it right. So they conceived of the XCON system. It was shortly said to save millions of dollars per year for digital, and it launched the AI biz. You couldn't go to a party and say you were in artificial intelligence without a venture capitalist calling you the next day. So it was all about rules. It was all about capturing the intelligence of the human configurers in the form of rules that had a very simple structure. Everything was in the form of a if and a then. Now, I don't imagine any of you have been professional computer configurers. How about, so what I'd like to do is I'd like to explain the idea in a different context. I imagine that many of you have been professional grocery store baggers. Is that right? No? They don't bag groceries? I guess in Wellesley you have to bag your own groceries. No, but who's been a grocery store bagger? Nobody? You're all just too shy.
They're aspiring to be.
No. This RSDigital stuff doesn't work out. This will be a skill you can use.
They were waiting until you told them how to do that.
Well, probably most of you have purchased groceries at least, and watched grocery store baggers at work. Erica, how do you bag groceries? Can you tell me anything about it?
Heavy stuff on the bottom.
Heavy stuff on the bottom. Okay, let's see. There must be a few Andrews around here. I notice a big preponderance of Andrews. Where can I find an Andrew? Are you an Andrew? Yeah. What do you think, Andrew?
Putting things that are similar together, like put all your cans in one bag. Put your chips together.
Put the things that are similar together. Mm-hmm. See, well, here I'm kind of absorbing this. I'm a highly paid knowledge engineer, you see. And I've come to visit your site. And now I'm talking to the experts. Teresa, what do you think?
Put the fragile things on top.
Put the fragile things on top. Now, see, I'm getting all this stuff, but it's not in the if-then form. So as part of my highly paid knowledge engineering exercise, as part of my highly paid knowledge engineering activity, I'll just recast it in the form of if heavy, then top. So I just said it a little different way, right? But what I'm doing is I'm trying to massage it into a way that eventually ends up being computer manipulable. But you know what? You guys are all giving me very abstract stuff. Heavy, same, fragile. Well, let's get down into the grunge here. Can you tell me some more about Todd? Can you tell me something about bagging groceries?
Eggs are fragile.
Eggs. So what do you want to do with the eggs?
Because they're fragile.
See,
put them on the top.
No, he's too much. So, if eggs, then top. Boom! I'm earning my keep. See, anything else you can think of?
There's a problem if we buy only eggs.
Not at my grocery store. One bag per. What else can you say about this? Is that all you can say about this? Frozen stuff in bags. So, if frozen, then freezer bag. Okay. Well, why do you do that?
I don't know, actually.
Well,
to keep the other things from getting wet
When it melts.
a lot of people think that's one reason. So what it inevitably melts, it won't screw up everything else. There's a more scientific reason, of course, and that is that you want to basically bring all the frozen stuff together so the ratio of the volume to the area or something like that. Well, nobody's very polite. I guess. I guess you who are, was it you, Chris, who offered to keep like things together? Who? Was it one of the Andrews? I figure if I just say Andrew, if I get 10% chance of getting it right. So this isn't getting us anywhere. So I'm going to have to use the two principles of knowledge engineering in order to get some stuff that I can use in my program. So as knowledge engineers, you want to, you really want to absorb these two techniques, because not just because they help you to build rule-based expert systems, but because they help you to figure stuff out in general. So here's, these are just a couple of heuristics that constitute a powerful idea, namely how to figure out a domain that you don't know anything about. So let me peel off a little bit of board here and just write them down. There's the heuristic of specific cases. In order to deal with the fact that most experts, when you say, how do you do your job, they would just give you these abstractions. And the abstractions don't lend themselves to incorporation into a system. So in order to get the real experts out of the space of abstractions, you need to go to their site and watch them bag some groceries. Okay? Because when you see them actually working on specific cases, things will occur to them that wouldn't have occurred to them if they were merely talking about abstractions. So, for instance, nobody offered up a rule about what to do with the cereal. Nobody offered up a rule about what to do with the motor oil. Okay? Nobody said anything about the milk. It's not frozen. It's on the other hand, you probably don't want to put it upside down under a bunch of cans. Nobody said, well, I guess you did say something about the frozen stuff. But by looking at a specific case, you can you can elicit knowledge that you wouldn't have gotten any other way. Now there's a second heuristic, and that's the heuristic of strange differences. A term I just made up. But here's how it works. In looking at a specific case, you notice that the professional grocery store bagger does a certain thing with the frozen bird's eye whole green beans. But the next thing that comes along is a can of Stop and Shop green beans. And you, as the highly paid knowledge engineer, notices that the expert handles these two things differently. So what is the natural thing to do? It's the natural thing to do. You're from Mars, right? You don't know about anything yet. It could be that because one's from Stop and Shop, one's from Bird's Eye. All things made from Bird's Eye go in a sort of works, but mostly what you want to do is you want to say to the expert, these things look the same to me. They're both green beans. Why did you handle one differently from the other? And so the instantaneous response will be, well, I put all the frozen stuff in a freezer bag. So what comes out of this is a piece of vocabulary that you need in order to build an expert system that does that job. It's the vocabulary of is it or is it not frozen. So the heuristic of specific cases gets the expert to tell you stuff they wouldn't think of otherwise. And the heuristic of strange differences helps you to figure out what the vocabulary of the domain is. Okay? So, as a highly paid knowledge engineer, using these two heuristics, it's possible to go into a domain like the configuration domain, and instead of conceiving rules that bag groceries, you conceive rules that configure computers. So what's the right picture to think of when you think of a rule-based system that looks like that kind of system, a bagger system or a configuration system? Well, if I were to see, here's a little logo for a problem-solving idea. Here's the corresponding logo for the idea we're talking about. There's some box that has state. That is, that they're variables and arrays and data structures that tell you how many bags there are, what stuff is in the bags, what stuff is remaining to be bagged. That's a state. And looking at that state are a bunch of rules. I'm going to draw them as AND gates, a symbol familiar to electrical engineers, because these little pieces are looking for their conditions to be satisfied, and if their conditions are satisfied, they change the state. So it's just a little loop like that. But importantly, all of the knowledge is cast in the form of if this, that, and the other thing, then do this. All right? Now that's a system in which actions occur. These actions could be, they are in fact changes of state. So things can get written and things can get erased. Right? But these kinds of systems are often used not as a way of specifying what happens, but as a way of specifying conclusions. They're often used as deduction systems. And the curious characteristic of a deduction system is you can't erase. Why can't you erase a deduction system? Well, because if something's true, it's always true. You can't say that something is both true and false at the same time. And mostly time is not a factor in these deduction systems, so therefore if something's true, it's always true. So mostly, no. Many times these rule-based systems are cast in the form of deduction systems. And Meissen was a deduction system. It was a system that concluded what kind of disease you have from the facts at hand. It didn't do anything. There were no actions. It just looked at the evidence and formed conclusions based on the evidence. It might conclude that you have primary bacteremia or some damn thing like that. Well, the trouble with mycin is that we're not doctors, at least I'm not, and therefore primary bacteremia doesn't roll easily off my tongue, and I don't know any of the rules. So if we're to understand how these deduction systems work, we need to do the same trick we did with the configuration for XCon. We'll find some simple thing we all know about that runs in parallel with respect to what it does. And that thing is just identifying animals in a little zoo. Not a big zoo. We don't want we don't have to do too much work, but you might imagine that we could write a system of rules that would be useful in identifying animals in a zoo. And then since I'm from Mars, I might ask you questions about, this thing is a cheetah and that thing's a giraffe. What's the difference? They look the same to me. They kind of got the same color and they both got spots in the forelegs. And what's the difference? One's got a long neck. Is that enough? Wait a minute. There's other things that distinguish between a cheetah and a giraffe. And so on and so forth. We could do that. We could use those heuristics. So let's assume we've done that. We might then conjure up a few rules. So here's one. If this creature eats meat, then it's a carnivore. Simple rule. And can you think of another one that would give us carnivore?
Incisors?
Ah! Eve says teeth. Actually, her name is Donna, but she's with all those apples. So let's see, that we got teeth. And then we might buttress that a little bit by looking at claws. And then if we want to be sure, we might put a restriction on the eyes. Carnivores like to have eyes that point forward. Things that get eaten like to have eyes that point out that way. So it suggests what kind of animal we are, doesn't it? All right. So there are a couple of rules. And then if we want to recognize a cheetah, we might say, well, it has to be a carnivore. And it has a certain kind of spots and a certain kind of color. So now we have three rules in a little system that recognizes zoo animals. Should we do this? Just run a little program that does this. So let's have our first effort at making that thing work. I take it this thing takes a little while to warm up.
While it's warming up, are there any expert systems using medicine?
The question is, are there any expert systems that are used in medicine now? Few, if any, for legal reasons, mostly. Yeah, there are programs that will do a reasonably decent job of analyzing a cardiogram and things of that sort. But for the most part, mycin never made it to the medical world because of legal liability issues and because, in the end, it didn't solve a problem. Because figuring out exactly what you've got wrong with you is not a problem that anybody cared about. They just know you're sick, boom, broad spectrum antibiotic, and get on to the next patient. There is, however, a very wonderful program, which I wish to hell were commonly used for doing genetic counseling. So you describe your family history, and it tells you what dangers there are with respect to various genetic diseases, such as, for instance, hemophilia, Tay-Sachs disease, and so on, with exact probabilities. Well, another of the Bayesian applications of artificial intelligence. It's interesting, by the way, how these things often intersect with social questions. The program that does genetic counseling has a undesirable byproduct of frequently demonstrating that somebody you thought was a relative actually isn't. So there's a little set of things we might know. And by the way, now you know, well, let's see. No. Well, I'll save that for the next demonstration. If I just click on deduce here, you can see that the first thing that's deduced is that because the thing has hair, it must be a mammal. So there's a rule that says that. It happens to be Z1. And you can just go through here and see that the carnivore rule has been triggered, so we know the Swiftie is a carnivore. And because of the spots in the color, he's a cheetah. So let's initialize another one. Splashy. Feathers means as a bird. A whole set of things means as a penguin. Then nothing else is deduced. Stretch. So we had a cheetah. Let's see what this guy is. It's a mammal. Bozo is a bird. Stretch chews cud. Stretch is a giraffe.
Who's Bozo?
Where'd Bozo come from? Well, you got two animals here in their database. So it's not enough to have the rules written down in the form that I've done it. We have to have variables. So X eats meat means that X is a carnivore. So if we come in here with Bozo and Swiftie, we're not going to get them confused. We're not going to assert that Bozo's a giraffe just because Swiftie is. That's because we've got variable bindings all over the place. So the X has teeth, X has claws, X has eyes, and so on. Means that X is a carnivore. So the X's are all variables. And if we were being precise, we would have a language with question marks or something, and it would be readily translated. So this is X is a carnivore, and X has spots, and X has a color. It means that X is a cheetah. And you don't get confused because you've got the variables bound. Bozo. Swiftie has hair. It means Swiftie's a mammal. Swiftie is a carnivore. Swiftie is a cheetah. Bozo's a mammal. Bozo's a carnivore. And Bozo's a cheetah. That's because Swiftie is a parent of Bozo. And you are what your parents are, mostly. There are some exceptions, of course. You know the exceptions. Doesn't work if you're a mule, but for the most part, you are what your parents are. So there's a little simple rule-based expert system that starts with some facts and moves forward through the facts, making conclusions. But you know what? It's important to notice that as you use such a system, these things all link up. Oh, I don't know if it's in the examples, but you can certainly imagine a system in which some initial considerations of teeth, claws, and eyes dictate that the thing is a carnivore, and then that becomes part of the input to the next rule. Right? So we're moving from facts to conclusions. And this may go forward several layers. So that we introduce now an important term, forward chaining. We're moving forward from facts toward conclusions. Okay. Now, you're all computer scientists, nearly graduated from Mars Digital University, so you can easily imagine building a system like this and then having the system leave behind a trace of everything it did. Right? So if it used Rule 7, I just made it up. If it used Rule 7, God knows what it really is, in the course of demonstrating that a particular animal is something or another, then you can look at the trace and see where it was used. And this makes it possible for you to do something you never do with a program that's not rule-based, because this endows your program with the capacity to answer questions about its own behavior. Because now you can say, oh, I see the system concluded that our animal is a cheetah. How did it do that? Well, it goes into the trace and notes that it did that by Rule 7, which called upon knowledge of carnivore, spots, and color. So that's an example of dealing with a how question. I could ask another question. I could say, why was it important to know about teeth? For which it will go in and identify that portion of the trace. Let us call it Rule 2, just so I'll have a handle to use in my description. It'll go in and say, oh, I see Rule 2 used teeth. And Rule 2 made a conclusion about the animal being a carnivore. So the why question is answered by going the other way. How says find the place and go to the left. Why says find the place and go to the right. So this program can answer questions about its own behavior because it's rule-based. So now, what I want to do is I want to leave this topic alone and do another little demonstration. I want to reach way back into ancient history, back to the Renaissance, and show you a modern version of Wintergrad's Blox World program. And after we've discussed it a little bit, we'll bring it all the way back here into our discussion of rule-based systems. I always counsel people about turning the lights down low. I always lose about 5%. Nevertheless, we'll turn them down a little bit. Exceptions prove the rule. This is actually a program that does a whole bunch of things. It's got a version of ELIZA built into it. My version of Wintergrad's program does, I mean. So I could say myself. I don't know. Can you read that? Let me make this up a little higher so you can see it. Probably take pretty good eyes to see that from the back, but that's the penalty for sitting over there. Okay, let's see. Damn. So you can go on and play with this stuff a lot. It's great fun. But the Wintergrad system, although curiously enough, it uses language technology enough like ELIZA to run in the same system, was about something else. Let's see. Oops. There we go. Now, Wintergrad didn't have brilliant colors. He was working with a black and white display, and his thing was three-dimensional and stuff. But essentially, this gives you the idea. I don't know if this will work, by the way. Yeah, I guess it does. I was a little worried about code rot, but you notice that in this particular case, I just named the blocks that I wanted to be moved. So now I could say put the wide green block on the big red block. Cross your fingers. Ah. Mm-hmm. But the part of the program that I want to exercise is more like this. Boom. If it were a person, we would have cheered. If it were a child, we would have said congratulatory and endearing things. Because it didn't do anything with B4. It was smart enough to move exactly those blocks that it needed to move and not disturb anything that it didn't. So how would you build a program like that? Do you know how to build a program like that yet? Maybe you do. I don't know. Maybe you're a genius that you had only been born 30 years earlier. You could have gotten Winograd's thesis instead of him. But this is a program that wowed everybody in 1970 when it was written. Partly because of its language interface and more because of the public relations impact of this little blocks world program that can manipulate blocks. Now, in some ways it was less impressive because it wasn't in glorious color, but in some ways it was more impressive because it was a sort of three-dimensional blocks world with a little area rather than a two-dimensional blocks world that I've hacked up here for this demonstration. But how does it work? Could it answer questions about its own behavior? Let me show you how it works. I hate to see it go. Well, I don't know. I'm afraid some of these golden words will have to disappear under layers of other words. I want to show you the program structure. There's a put-on program that makes 4 calls. It finds space. It grasps. It moves. And ungrasps. Not horribly surprising, right? That's what you do when you move a block around. Oh, man. This drives a stake through my heart to erase this. But what can we do with limited board space? In order to grasp something, the program says, well, I'm a one-handed robot. I can't grasp anything unless there's nothing on top of it. So I make a call to a program called ClearTop. We'll do it in the scheme way, using hyphens instead of the Java way of using underscores. Now, how do you clear the top away, clear all the junk off of something? Well, you get rid of the stuff that's there. Something's called a get rid of. And how do you get rid of something? Well, you move it to some location on the table. How do you do that? Well, you have another call to put on. Boom, this program is now recursive. How do you find space for something? Well, if there isn't any space, you call get rid of until there is space. So you don't have to clear everything off in order to find a space. It's going to take a lot of courage, and I actually haven't tried this, but you look puzzled. Let me see if I can make this work. So, with luck, it won't get rid of B1. You'll know it's got room. Phew. Never before tried with this program. It's I like to show how macho I am sometimes. So that's the structure of the program. That's all there is to it. So, how do we understand the program? Well, we make a trace. We show we trace its behavior on a problem. Oh, damn. So here's the problem. I'll put block A on top of block B. So off we go. According to our program structure, there are 4 calls. And this one's, I guess, a find space A, B. How does it grasp? Well, it must have to clear top. How does it clear the top? I guess it has to get rid of D. C. I just did that to make sure everybody's awake. Get rid of C. How does it do that? Put C, well, I guess we'll call this program put on C table. How does it do that? 4 little things to do there, including grasp, C, and how does it grasp it? Well, first of all, it has to make sure it's got a clear top, and so on it goes. So if there were not just one thing up there, but a whole stack of them, this would, eventually get them, go recurse all the way down till it picks off the top one. So that's a little trace of the program in action. Now suppose I keep this trace, being a big computer scientist, and now ask a question: why did you clear off the top of A? I go in here and I reference the higher level element in the trace. Now suppose I say, how did you clear the top of A? Go into the trace and reference the thing below. So now I've got a program that can answer questions about its own behavior by keeping a trace of what? The subroutine calls? Yeah, basically. But they are subroutines that are organized around the goals of the program. That's the trick. So now my trace of subroutines is exactly corresponds to a goal trace that's meaningful to me, the human. So now I can say, how did you grasp A? By clearing off its top. How did you clear off the top? By getting rid of C. How did you get rid of C? By putting C on the table. How did you put C on the table? Well, by finding space, grasping, moving, and ungrasping. How did you put C on the table? By getting rid of C. Or why did you put C on the table? To get rid of it. Why did you want to get rid of it? To clear its top. Why did you want to clear its top? To grasp A. Why did you grasp A? Because I want to put A on B. Why did you want to put A on B? Because you told me so. Okay. And what about when you fall off the other end? Oh, I just did it. When did you get rid of C? While I was putting A on B. So just by rummaging around in the goal tree, left behind by the subroutine traces, you can answer questions about the behavior of the program. Oh, sorry, is it Joe? Jeff. There are 2 Jeffs. You're Jeff. Isn't he Jeffrey? Yeah.
How did it know to put C on the table and not on B?
By convention. By convention, when it's getting rid of something, it puts it on the table. Well, it must strike you as being curious that we could answer questions about this program and we could answer questions about that program. So we can use rules and forward chain, or we can build a program around the idea of goal-oriented subroutine calls, and we can answer questions about the behavior of both of them. So it must be that there's something that they have in common. And so we say, well, what do they have in common? Well, what they have in common, I've already said. They both involve a goal tree. What's a goal tree? Well, it's a representation of how problems are connected together. So abstractly, that dot is a problem. And that may be connected to a subproblem, such that if I solve this, then that is solved automatically. But usually, a problem is connected to multiple subproblems, such that I have to solve all of them in order to have the superproblem solved. Sometimes, in order to solve the superproblem, it's enough to solve any of the subproblems. And now I better find a way of distinguishing these. We'll call this an AND node. And we'll call this an OR node. And we'll put this arc across these. Sort of looks like an A, doesn't it? It's an AND node and an OR node. So we can imagine then with a rule-based expert system forward chaining, or with a program subroutining its way through its solution, what we do is we connect these pieces together, and what we're left with is some kind of tree structure that supports question answering. So what do we call this guy? Well, we could call it an AND OR tree. Or we could call it a goal tree. Or we could call it a problem reduction graph. Same thing in all cases. If I hadn't destroyed my definition of artificial intelligence, I would be able to come back now and say what this is all about. What this is all about is a representation of how problems are connected together that provides us with the constraint that we need to execute algorithms that solve problems, that make deductions, that bag groceries, diagnose infectious diseases of the blood, and thousands of other things that have been done with systems built this way, mostly rule-based expert systems. So this whole works this morning then is about a very simple representation of how problems are connected together, which supports a lot of hair about hairy algorithms that use the constraint that comes out of this representation. But to see the red thread, this is at the bottom. This idea that problems are related together by simple everyday human notion of problems being solved by dealing with subproblems. Let's do this once and for all and create a shell that allows us to type in rules in some simple English-like format that will do different things according to the rules that we pump in. So the same interpreter, to use the scheme language, the same interpreter can be used to run any kind of expert system you want. It could run one like this, which is a forward chainer, or it could run a backward chainer, a word we haven't discussed. Let's discuss backward chaining for a second. You know what it is already, right? I mean, it just uses the rules going the other way. Instead of working from facts toward a conclusion, you start with a hypothesis. You say, is this animal a cheetah? And you say, well, he's going to be a cheetah if he satisfies these criteria. How do you determine if the carnivore criteria is satisfied? Well, I got a rule that does that. Let me see if he has teeth. Nope, I can't see his teeth. He's got a mouth shut. Well, let's try another rule. Let's see if he's eating meat. Great. He's eating meat, so we know he's a carnivore. So we work from hypothesis back to see if we can establish, perhaps by way of a whole chain of rules, that certain facts support it. So that's the opposite of forward chaining. That's backward chaining. So you can have, now to come back from my recursion, you can have a shell that works in either forward or backward, in either a forward or backward direction. That's okay. So you can build a system. It's an interpreter for rules. The rules might look like this. We can put some parentheses around it, make sure they look like scheme. Then there might be some other clauses here. I'll just indicate with some dots. Then and now, just to make it one little package, I'll give it a rule name. Call it Rule 1. And there we have it. There we have a machine digestible version of the carnivore rule. And we could build a rule-based interpreter, which we'll call a shell, and sell for $75,000, that will absorb these rules and run them for you and give you pretty graphics. And people offered such shells in the 80s, and people bought them. So they were basically offering you a programming language that was a rule-based programming language. So everything you wanted to say had to be said as a set of rules. So how would you get two rules to fire in succession if you were using such a shell? Because all the rules are doing is sitting around waiting for their conditions to be satisfied, at which point they fire. Maybe more than one is satisfied at the same time, so you need an elaborate set of conventions about who gets to fire if multiple rules are fired at the same time. But how do you get Rule 1 to fire, or Rule 2 to fire right after Rule 1?
If axes meet and Rule 2 is true.
Gary, right?
Doug,
sorry. Doug says that Doug's essentially got the right idea. What you do is you have Rule 1 assert some symbol that Rule 2 is looking for. So the then might include another clause, fire Rule 2. And then when Rule 2 sees that, it says, aha, it's time for me to do my thing. You notice that we basically kind of tricked it into doing the right thing? It's kind of screwy because in an ordinary programming language, you just write statement 2 after statement 1 and it gets executed after statement 1. So in order to get this rule-based system, this rule-based programming language to do the right thing, we sort of had to trick it by some little device that asserts and watches for some special sequencing symbol. So this leads to a fundamental question. Who are the rules good for? The knowledge engineer or the programmer? Digest that for a moment and let me tell you why a rule-based system can be a good idea. It can be a good idea because if all of your knowledge is uniformly expressed in terms of rules, uniformly expressed in some syntax, then it's possible to build a superstructure on top that does glorious things for you. For example, we've already shown that if you keep a trace of how those rules fire, you can build a system that answers questions. You might even be able to build a system on top that learns rules, and then you've got your database for free. You might be interested in building a system for debugging. For which your Q&A subsystem would be a very helpful piece. You might want to build a system on top for some kind of graphics suite. And so on. So having all of your knowledge expressed uniformly can be of great benefit. On the other hand, it can be an enormous pain too, if you want to do some simple things like ordinary sequencing. So what's the answer? Are rule-based shells a good idea or not? And as in the real world, the answer is both have advantages. I often, in the middle 80s, would say to someone, I see you've been using such and such a company's expert system shell. Do you like it? It's wonderful. It's great. I said, that is interesting. Why is it so good? He said, well, it enabled us to build a system that could do something that we've never been able to do before. I said, wow, that's terrific. I'm really glad this rule-based expert system technology has been so helpful. How many rules are there in this system? 3. So what was clear is that the rule-based expert system idea wasn't helping them as programmers. Because, we know about if else, right? It was helping them at a conceptual level to organize the knowledge about the domain. So you use a shell when you have 300 rules, 10,000 rules. But if you have 3 rules, then it's just a few lines of code. But it's the way you think about the problem that's encouraged by the rule-based expert system idea, and in particular by this way of representing the connection between problems and subproblems, that's important. And you say, well, wow, is that all there is to that? Can that possibly make something intelligent? And the answer is yes. I mean, when you first look at that Blox World program, you look at that, and everybody's so jaded today. If I walked in naked, nobody would probably notice it. But back in the 1970, when that was first done, it looked really cool. It looked like it was really, really intelligent. But when you take it apart, all you see is a gold tree. So this is an important thing I like to sort of stress. Once you see how an so-called intelligent program works, its intelligence tends to vanish before your very eyes. By the way, this is true of people too, right? Once you see how they solve some hard problem, their intelligence seems to evaporate. My favorite example is the discovery, to allude to it yet again, the discovery of the structure of DNA. Watson, who is simultaneously the world's greatest textbook writer and the world's greatest scientific mystery writer, tells us that he completed the discovery with a step that involved cutting out from cardboard some shapes that corresponded to the 4 bases and finding out how they could fit together. Now, solving a 4-piece jigsaw puzzle is not something you would associate with great genius. And so your immediate reaction is, I could have done that. But realizing that the thing to do was to cut out 4 pieces of cardboard and see if you could fit them together was where the genius lay. And that's why he fully deserved getting his share of that Nobel Prize for discovering the structure of DNA. But it's an example of how once you see how a human solves a problem, your immediate reaction is, that's not very intelligent. I could do that. See that nice little twist there? That's not very intelligent. I could do that. So that concludes what I want to talk about this morning. By way of summary, I wanted to give you a little flavor of where AI is and where it's come from. I wanted to offer to you this rather newish, one-day-old way of looking at what AI is, thinking of it not as just a collection of algorithms, but rather as a subject which deals with a certain class of representations that expose a certain class of constraints that enable a certain class of algorithms. But it's not the algorithm that matters, it's the constraint that matters. Once you've got the constraint exposed by the representation, then you can do miracles with all sorts of algorithms. You can write a program, you can use rules, there are all sorts of things once you've got the constraint exposed by the representation. But until you've got that, solving a problem can be a horror show. It's like trying to build a big system without the model view idea of how to fit big systems together. You can do it, but it's just much easier when you've got the right concept in your head. Yes, Samuel.
Can you just say a little bit more about constraints?
Well, algebra, when we talk about algebra, we're talking about a certain kind of constraint. And constraint, I mean, it's a word that just means holding things together, and it's a word that we'll be using often in the next few days. And I think as you see other kinds of constraints at work, the concept will be clearer. By constraint, I just mean one thing is limited by another. Let me give you an example that will come up tomorrow. Suppose that I want to color a map. And I know I can do this. Some smart mathematician has demonstrated I only need 4 colors. Let's call them red, green, blue, and yellow. As soon as I say I'm going to choose red for that constrains what I can do at the other places. if I have a schedule, I've got 10 airplanes and a schedule to fly. The places I have to fly around to constrains what aircraft I can use on each leg. If I have a drawing, it's just a drawing of maybe a block. My knowledge about this junction limits my interpretation of the junction in the center. So in all the examples I've talked about, we're talking about how knowing one thing limits what can happen in another place. Or perhaps exposes a regularity that I can make use of. So that's roughly what I mean by constraint, and ask me every day until it's clear. Byron? Is it Byron?
Brian.
Brian, sorry.
So I'm wondering, you seem to be going out from the algorithm to the sort of defining the nature of the problem, but I wonder if there's not another layer outside of that which has to do with motivation and what drives us to solve particular problems in the first place, that has a motivating, or rather that has a role in intelligence. I'm wondering how that fits into something you just sort of zoom out of the way.
Brian, right? Question is, how do you figure out what problem to solve? Well, of course, if you're a computer professional, it's usually handed to you. But even that is not so straightforward. In the 80s, when we had the first explosion of AI technology, idiots, including me, would wander around telling people how to choose problems. And what we told people wasn't very good. Because what we told people was choose problems that fit the technology instead of the other way around. AI has done much better when AI has been applied to what the business people will call mission critical types of problems that people care about. In the early 80s, everybody figured everything was so hard you had to pick problems that were suited to the technology, so people wrote a lot of systems that nobody cared about. But when you asked the question, it sounded to me like you're asking a science side question, which is the question of how animals, humans in particular, pick what problem they're going to work on. And that is a very interesting and difficult question that has to do with attention, has to do with goals, has to do with the interaction of our brain pieces that we share with pigs. Let's say the limbic system and all those kind of deep structures, how they rear their lovely heads and tell us at a higher level what they'd like to see get done, whether we ought to get fed or go to sleep or whatever. And we know almost nothing about that. Your question does, however, stimulate me to make the following claim. When we get this all figured out, what we will find, I believe, is that most of what we do as humans is done by abstracting off of the world in which all animals live. And in particular, it's abstracting off of worlds like that, where we have objects moving around in the space under the control of agents for purposes. Once we understand how to do that, I think everything else is done by abstraction. When I say, let me give you a lecture, it's almost as if ideas were flowing around in some space. And I believe that we understand that in virtue of our ability to do analogies between those abstract spaces and simple physical worlds. Why do we do it? Well, because our attention is driven to it. Why is that? We don't know. Are there any other questions before we break for the morning?
Just a quick, the representations, I understood them in your example, the farmer, the fox, the goose, and the grain. Maybe if you could point out how what the representations were in this example, the block.
Yeah, that's the question is what are the representations? Well, here it's a trace of subroutines, but I'm making the claim that this is a special case of problem reduction nodes, and this is the fundamental representation I claim is uniting all of our stuff today. A problem reduction node, I think perhaps I'm calling it that for the first time now. A problem reduction node is something of which a rule is a special case. It is a fragment of a problem reduction tree. It is something on which we can form a problem reduction node. The subroutine trace is something on which we can superimpose a problem reduction node. So it's the fact that these things leave behind or make use of these fragments and stick them all together. It's the sticking of these problem reduction nodes together that make all these systems work, and that is the fundamental representation. Other questions? Samuel?
We'll leave us hanging on the 10-year revolution.
We'll discuss that as we go downstream. We'll discuss that a little bit this afternoon as well.